Welcome to the Deep Dive, the show where we cut through the noise and get straight to the essence of groundbreaking research.
That's right.
Today we're plunging into a topic that's buzzing across the entire machine learning landscape: the evolution of large language models beyond mere text generation.
Yeah, into something far more dynamic, what's being called agentic intelligence.
Exactly, and our focus is Kimi K2.
And Kimi K2 represents a significant milestone in this paradigm shift.
Right.
It's not just another language model. We're talking about a 1.04 trillion parameter mixture of experts large language model.
Oh, wow.
Our entire discussion today is grounded in its recently published technical report on ArcSUF, offering a foundational look at its innovations.
Okay, so our mission today is pretty straightforward. We're diving deep into this groundbreaking paper, pulling out the core ideas about how Kimi K2 is built, how it learns, and what it can actually do. We want to give you the real professional lowdown, helping you understand not just what Kimi K2 is, but how it's truly pushing the envelope for open source agentic AI.
Let's do it.
Let's get right into it. All right, we've used the term agentic intelligence a few times already. For those of us deep in machine learning, what exactly does that mean for large language models in this context?
Okay, so at its core, agentic intelligence refers to the capability for models to autonomously perceive, plan, reason, and then act within complex dynamic environments.
Act. Okay.
Right. This marks a profound departure from traditional static imitation learning, where models simply mimic patterns from their training data.
Just repeating what they've seen.
Exactly. Instead, agentic models actively learn through interactions, acquire new skills that might be entirely outside their initial training distribution, and continuously adapt their behavior through ongoing experiences.
So it's not just about what they've been trained on, but what they can do and learn to do on their own. That sounds like a fundamental shift in how we think about AI capabilities.
It really is.
What's the deeper implication here?
You hit on the key insight. The core belief is that this approach allows an AI agent to, transcend the limitations imposed by static human-generated data.
Go beyond the data set.
Precisely. By exploring and exploiting environments, the agent can potentially acquire superhuman capabilities. This is exactly why agentic intelligence is rapidly emerging as the defining characteristic for the next generation of foundation models.
Right.
It has wide-ranging implications across diverse applications like complex tool use, sophisticated software development, and even real-world autonomous systems. It's about enabling truly adaptive and self-improving AI.
That's a huge scope for impact. So how does Kimi K2 position itself within this new frontier? Give us a snapshot of its scale and the challenges it aims to address.
Okay, so Kimi K2 is specifically designed to tackle the challenges in achieving this level of agentic intelligence. It's an MoE LLM featuring 32 billion activated parameters within a staggering 1.04 trillion total parameters.
A trillion, yeah.
The development team identified two primary challenges they had to overcome. First, during pre-training, there were issues like optimizing token efficiency and grappling with the increasingly limited supply of truly high-quality data.
The data bottleneck.
The data bottleneck, exactly. And second, in post-training, the difficulty lies in effectively scaling agentic capabilities. Things like multi-step reasoning, long-term planning, robust tool use.
The complex stuff.
The really complex stuff, because these behaviors are inherently rare in natural human-generated data, and thus incredibly costly to scale up from scratch.
It sounds like they've gone after some foundational hurdles. What are Kimi K2's core contributions that help it achieve this kind of agentic capability?
The paper highlights three primary contributions that truly stand out. First, there's the muon clip optimizer. This is a novel optimizer that integrates the token-efficient muon algorithm with a stability-enhancing mechanism they call QK clip.
Okay.
And the remarkable outcome is that Kimi K2 was pre-trained on an immense 15.5 trillion tokens with zero loss spikes.
Zero.
Yeah.
That's unusual for this scale.
It's a significant feat, yeah. For models of this scale and complexity, achieving that signals unprecedented training stability.
Okay. Zero loss spikes over 15.5 trillion tokens. That's incredible stability for such a massive training run. What's the second key contribution they emphasize?
The second is a large-scale agentic data synthesis pipeline.
Okay.
This pipeline systematically generates high-fidelity, verifiably correct tool use demonstrations. It achieves this through a clever combination of simulated and carefully curated real-world environments.
Ah.
creating precisely the kind of structured, high-quality agentic trajectories that are essential for effectively training these complex behaviors.
So they're not just relying on existing data sets, but actively creating the precise data needed to teach these complex behaviors. That sounds like a fundamental shift in how we approach data.
It really is.
What's the deeper implication here for the future of LLM training?
You got it. The insight is we're moving from a passive consumption of scarce human data to proactive, intelligent data engineering.
Right, engineering the data itself.
Exactly. This doesn't just augment volume. It allows us to sculpt the exact kind of high-quality, structured interaction patterns needed for agentic AI.
Patterns that just don't exist much in the wild.
They simply don't exist in sufficient quantities in raw web data. It's
Yeah.
about designing data to train specific intelligent behaviors, not just language generation.
That's a powerful idea. And the third core contribution.
The third is a general reinforcement learning, or RL, framework.
Okay, RL.
This framework combines verifiable rewards, what they call RLVR, with a unique self-critique rubric reward mechanism.
Self-critique. Interesting.
Yeah, it's particularly innovative because it allows the model to extend its alignment beyond static datasets into more open-ended domains. So it learns not just from external signals, but also from evaluating and refining its own outputs.
That brings us to performance. When we look at the headline numbers in the paper, figure 1, I think, how does Kimi K2 Instruct stack up against other models, especially in those crucial agentic capabilities?
The performance overview is quite strong. Yeah, figure 1 really encapsulates it. Kimi K2 Instruct achieves state-of-the-art results among open-source non-thinking models.
Non-thinking. Okay, so that's a direct comparison.
Right, no extra inference steps. And what's truly significant is how effectively it closes the gap with leading closed-source systems like Claude 4, Opus, and Sonnet. It indicates a really competitive standing.
That's promising. Can you give us some specific highlights? Which benchmarks truly demonstrate its prowess?
Absolutely. The top-line performance shows its broad capabilities. For agentic task, it scores 66.1 on TOG2 bench and 76.5 on ACE bench English.
Setting a new bar for open models there.
Yeah, definitely. In software engineering, which is a key agentic application, it hits an impressive 65.8 on SWE bench verify.
Oh.
And with multiple attempts, it reaches 71.6%, coming remarkably close to Claude 4 Opus's 72.5%.
Very close.
It also leads all models on LiveCode bench V6 with 53.7%. Right. Across general domains like coding, mathematics, and reasoning, Kimi K2 performs exceptionally well too. For example, 49.5 on AMI 2025 and 75.1 on GPQA Diamond.
And these are all without those extra thinking steps.
Correct. All achieved without additional inference time thinking steps, making the comparison quite direct and impressive.
And crucially, the paper mentions strategic open sourcing. What's the significance of that for the broader ML community?
Right. The team is strategically releasing both their base and post-trained model checkpoints. This is a deliberate and, I think, incredibly important move.
Why is that?
Well, it's designed to democratize access to these cutting-edge agentic capabilities. It should spur future research and applications in agentic intelligence within the broader community.
So giving people a foundation to build on.
Exactly. It provides a powerful, high-performing foundation for others to build upon, accelerating the entire field's progress.
That gives us a great high-level view of Kimi K2's agentic ambitions. Now let's peel back the layers and understand how they built this powerhouse from the ground up, starting with its pre-training innovations.
Okay.
You mentioned the Mean Clip optimizer as a key contribution. What's revolutionary about Mean Clip and why was it necessary?
Okay, so Kimi K2 was pre-trained using the Muon optimizer. It's known for being token efficient, includes weight decay, consistent update, RMS scaling, all that.
Right, from their previous work.
Exactly. Moonlight showed Muon substantially outperforms Atom W in token efficiency. However, scaling Muon training up to this magnitude revealed a significant challenge: training instability.
The dreaded instability.
Yes, specifically due to exploding attention logits. They actually observed this issue more frequently with Muon compared to Atom W.
And standard fixes didn't work.
Well, existing strategies like logit, softcap, or query key normalization were either insufficient or just not applicable, especially with multi-head latent attention, MLA.
Why not with MLA?
Because its key matrices aren't fully materialized in a way that allows for standard normalization. So yeah, the problem is a constant headache for anyone wrestling with large-scale training.
So Muon was efficient but inherently prone to instability at this scale. How does QK-Clip address this specific problem of exploding attention logits?
QK-Clip is a novel weight clipping mechanism designed to explicitly constrain these attention logits. The core idea is pretty neat. It rescales the query and key projection weights after each update.
After the update.
Yeah, but only if the per-head maximum attention logit exceeds a predefined target threshold. Let's call it tau.
Okay.
What's clever here is that this clipping doesn't alter the forward or backward computation in the current step.
Ah, so it doesn't interfere immediately?
Right. It merely uses the max logit as a signal to gently control weight growth in subsequent steps, preventing those runaway values.
And it's applied per head. Can you elaborate on why that specific fine-grained application is so important?
Right. That's key. Instead of a naive implementation that clips all attention heads uniformly, which should be overkill, they determine a per-head scaling factor.
So it's targeted.
Very targeted. This minimizes intervention on model training, because often only a small subset of heads might actually exhibit exploding logit.
Makes sense.
And for MLA, they apply clipping specifically on the unshared attention head components. The query and key parts get scaled based on their specific contribution, while shared components, like the rotary part, are left untouched.
To avoid side effects.
Exactly. To prevent unintended side effects across heads. This surgical minimal intervention approach is key to its effectiveness without degrading quality.
That's a fascinating level of detail in the optimization. So UnonClip essentially integrates the token-efficient muon optimizer with weight decay, RMS matching, and this new QK clip mechanism. Did they validate its effectiveness in keeping training stable?
Absolutely. The paper presents compelling empirical validation using figures 2 and 3. They first showed that a vanilla muon run on a mid-scale model like 9 billion activated, 53 billion total parameter MOE rapidly caused maximum attention logits to exceed 1,000.
Way too high.
Yeah, that level of logit explosion is a clear indicator of potential instability, often leading to lost spikes, maybe even divergence.
Okay, and with MuonClip?
In stark contrast, Kimi K2's training, utilizing MuonClip with tau set to 100, showed that max logits were effectively capped right at 100.
Capped perfectly.
And over the entire 15.5 trillion token training run, these logits smoothly decayed to a stable range. Critically, the training loss curve remains smooth and stable with no observable spikes.
Wow.
This empirically validates QK-Clip's robust and scalable control over attention dynamics. It just worked.
The paper also delves into why muon is more prone to logit explosion compared to other optimizers. Could you walk us through that explanation? It's in the appendix, I think.
Certainly. Appendix E provides valuable insight here. They found that muon's inherent update mechanism, specifically its M-sign operation, results in all singular values of the update matrix being equal.
All equal.
Yeah, meaning its effective rank is full. This is unlike Adams updates, which typically exhibit a skewed spectrum. A few large singular values dominate, leading to a low effective rank.
Okay, so full rank versus low rank updates. What does that mean for stability?
Well, weights trained with muon tend to exhibit higher singular value entropy, which increases the probability of singular vector alignment.
Okay.
And this alignment, when coupled with the attention mechanism's bilinear form, XIWQ, XJWK, which effectively squares the spectral norm of query in key matrices, it compounds any singular value increase.
So the attention mechanism amplifies the issue.
Exactly. Muon's tendency to enlarge singular values naturally translates into a higher risk of logit explosion in the attention mechanism. It's a deep structural reason for its observed instability at scale.
And the stability doesn't come at the cost of model quality, right? That's always a concern with such intervention.
That's a crucial point, and it's confirmed in Appendix D, Figure 12. They show that QK-Clip has negligible effects on the loss curve and does not degrade downstream task performance, even with aggressive clipping.
So it's safe.
It's safe and effective. The mechanism is designed for minimal intervention and, importantly, it kind of self-deactivates once training stabilizes and logit values are under control. It doesn't impede performance once the model is past that initial instability phase.
Beyond the optimizer, pre-training heavily relies on data. The paper discusses maximizing token utility. What does that mean? And how did Kimi K2 approach the data bottleneck of high-quality human data?
Right. Maximizing token utility means getting the most learning signal, or performance improvement, from each token consumed during training.
Getting more bang for your buck, basically.
Exactly. The challenge, as you alluded to, is the limited supply of truly high-quality human data. Simply repeating tokens while increasing exposure leads to diminishing returns and potentially overfitting.
So what did they do?
Kimi K2 addresses this through a novel synthetic data generation strategy, specifically a rephrasing pipeline. It's designed to amplify the volume of high-quality tokens without inducing significant overfitting.
Rephrasing. Interesting.
Yeah, it isn't just about creating more data, but creating more effective data.
So generating synthetic data is key. How did they apply this in practice, for example, for knowledge data, which often comes in long documents?
For knowledge-intensive text, where single epoch training isn't enough, but multi-epoch repetition has diminishing returns, they developed this synthetic rephrasing framework.
Okay.
It involves style and perspective-diverse prompting, using LLMs to generate faithful rephrasings of original texts. This ensures linguistic diversity while maintaining factual integrity.
How do they handle long documents? LLMs struggle with that sometimes.
Good point. For long documents, they use chunk-wise auto-regressive generation. Texts are divided into segments, rephrased individually, and then intelligently stitched back together to preserve global coherence.
Clever workaround. Figure 4 shows that, right?
Exactly. Figure 4 illustrates it. This cleverly mitigates typical LLM output length limitations. And finally, they perform fidelity verification.
Checking the quality.
Right, using semantic alignment checks between original and rewritten content. It's a rigorous quality control step to ensure the synthetic data is genuinely useful.
Did this rephrasing actually translate into empirical performance improvements?
Yes, empirically it did. Table 1 provides clear evidence. They tested this on simple QA. Repeating the original dataset for 10 epochs yielded 23.76% accuracy.
Okay.
Rephrasing the data once and repeating that for 10 epochs jumped the accuracy to 27.39%.
Nice improvement.
And even more impressively, rephrasing 10 times but only doing a single training pass still resulted in 28.94% accuracy.
Wow, so the rephrasing really helped.
Yeah, the accuracy consistently improved with more rephrasing, demonstrating the efficacy of their augmentation strategy. And they noted each original corpus was rephrased at most twice for these main experiments.
And what about for mathematical data? Did they use a similar approach?
For mathematical reasoning, their method was a bit different. They focused on rewriting high-quality mathematical documents into a learning note style.
Learning note style.
Yeah, drawing inspiration from the Swallow Math methodology, which emphasizes structured, pedagogical presentation, kind of like how you'd explain it to learn it.
Okay.
They also significantly boosted data diversity by translating high-quality mathematical materials from other languages into English, recognizing the value of cross-linguistic knowledge.
Smart.
So overall, the Kimi K2 pre-training corpus comprises a massive 15.5 trillion tokens of curated, high-quality data across web text, code, mathematics, and knowledge domains, all processed with rigorous validation. It's an enormous effort in data engineering.
That's a staggering amount of data, meticulously prepared. With that kind of advanced architecture and infrastructure in place, it's clear they had a solid platform. So how did they actually put it all together? Let's shift to the model itself. How is Kimi K2's architecture designed to handle the scale and achieve its impressive sparsity?
Okay, architecture. Kimi K2 is a 1.04 trillion parameter mixture of experts transformer model with 32 billion activated parameters per forward pass.
So 32 active out of over a trillion total.
Right. Its core design choices are similar to DeepSeek v3, notably employing multi-head latent attention, or MLA. The model has a hidden dimension of 7168 and a MoE expert hidden dimension of 2048.
The paper discusses a sparsity scaling law. Can you elaborate on the motivation behind increasing sparsity and how they implemented it?
Yeah, the motivation came directly from scaling law analysis. Their findings indicated that continued increases in sparsity, that's the ratio of total experts to activated experts, yield substantial performance improvements.
More sparse is better, basically.
Up to a point, yes. So they increased the number of total experts to 384, up from 256 in DeepSeek v3, while still activating 8 experts per forward pass.
8 out of 384, that gives a sparsity of 48.
Exactly, a sparsity of 48, which is quite high.
And what was the benefit of this increased sparsity? What did their scaling law analysis show?
They observed that under a fixed number of activated parameters, meaning constant FLOPs per token, increasing the total number of experts, and thus increasing sparsity, consistently lowered both the training and validation loss.
Better performance for the same compute.
Essentially, yes, as Figure 5 illustrates. The paper concretely states that under the compute optimal sparsity scaling law, achieving the same validation loss, say 1.5, sparsity 48 reduces FLOPs by up to 1.69 times compared to lower sparsities like 8, 16, or 32.
That's a significant saving.
It is. While there's a recognized trade-off with increased infrastructure complexity for higher scarcity, they adopted sparsity 48 for Kimi K2 to effectively balance performance and cost efficiency.
They also made a specific choice regarding the number of attention heads, reducing it compared to DeepSeek v3. What was the rationale there? considering DeepSeek V3 used roughly twice the number of heads.
Right. DeepSeek V3 indeed used roughly twice the number of attention heads compared to model layers, mostly for memory bandwidth and computational efficiency reasons.
So why did Kimi K2 go down to 64 heads from 128?
The main rationale was to significantly mitigate inference overhead, especially at longer context lengths.
Long context inference cost.
Exactly, which is crucial for agentic applications. For example, at a sequence length of 128K, increasing attention heads from 64 to 128 while keeping the total expert count fixed leads to an 83% increase in inference FLOPs.
83%? That's huge!
It is. And their empirical findings, shown in Figure 6, indicated that doubling attention heads yielded only a modest 0.5–1.2% validation loss improvement.
Not worth the costs.
Pretty much. That small gain simply didn't justify the substantial inference cost, especially given the more significant performance gains they were already getting from increased sparsity. Table 2 provides a good summary comparison of the architectures.
Beyond architecture, the training infrastructure itself is critical for a model of this scale. What were the key engineering innovations they employed for efficiency?
Okay, infrastructure. Kimi K2 was trained on an NVIDIA H800 GPU cluster. NVLink, NVSwitch within nodes, 8x400 GBPs ROSI interconnects across nodes. Pretty standard high-end stuff.
Right.
A key aspect was their flexible parallelism strategy. Instead of optimizing for just one specific resource configuration, they designed Kimi K2 to be trainable on any number of nodes that's a multiple of 32.
That flexibility sounds crucial for large-scale research and deployment.
It really is. It involved a combination of 16-way pipeline parallelism, PP, with virtual stages, 16-way expert parallelism, EP, and 0-1 data parallelism.
Okay, a mix of strategies.
Yeah, and this design ensures that each GPU holds approximately 30 gigabits for all the optimizer states and gradients, with the remaining memory used for activations, optimizing resource utilization.
How did they handle communication overhead, especially with expert parallelism? That often involves significant data movement, right?
It does. They implemented EP communication overlap with interleaved 1F1B. Basically, by increasing warm-up microbatches, they could effectively overlap that EP all-to-all communication with computation under the standard interleaved 1F1B schedule.
Overlapping compute and communication.
Exactly. This contrasts with approaches like dual pipe, which might need double the memory for similar overlap. To further mitigate pipeline parallelism communication overhead, they decoupled weight gradient computation from each microbatch's backward pass, executing it in parallel with the corresponding PP communication.
So hiding latency wherever possible.
Pretty much. This effectively overlaps all pipeline parallelism communications except the initial warm-up phase. They also adopted the smallest feasible EP size, EP16, to minimize EP operation time, giving Kimi K2's reduced attention computation. This also relaxed expert balance constraints, which can be a pain in MOE setups.
Memory is always a constraint with massive models, particularly for activations. How did they reduce the activation memory footprint to fit these huge models on GPUs?
Yeah, GPU memory for full MOE activations was indeed insufficient, as is common at this scale. So they used several activation reduction techniques.
Like what?
Selective recomputation was applied to inexpensive high-footprint stages, think layer norm, SweGLU, MLA up projections, MOE down projections.
Recomputing instead of storing.
Right. For activations that were less sensitive to precision, like MOE up projections and SweGLU inputs, they used FP8 storage, compressed to FP8 E4M3 to save memory.
But not computed in FP8.
Correct. FP8 wasn't used in computation due to performance risk they mentioned. And finally, and crucially, activation CPU offload was employed for all remaining activations.
Offloading to system RAM?
Yep. A dedicated copy engine streams the offload and onload, overlapping with both computation and communication kernels. This ensures that EP communication remains fully overlapped, as depicted in Figure 7. This multi-pronged approach was essential for fitting the model.
Now that we understand the architecture and infrastructure, let's talk about the actual pre-training journey. What was their recipe for this massive training run?
Okay, the recipe. The model was pre-trained with an initial 4,096 token context window using the mu-unclip optimizer and what they call the WSD, or warm-up stable decay learning rate schedule.
WSD schedule.
And a staggering total of 15.5 trillion tokens were processed.
15.5 trillion.
Yeah. The learning rate schedule had two main phases. The first 10 trillion tokens were trained with a constant learning rate of 2e4 after a 500-step warm-up.
Okay, stable phase.
Then followed by 5.5 trillion tokens with a cosine decay from 2e4 down to 2e5. A weight decay of 0.1 was applied throughout, and the global batch size was consistently maintained at 67 million tokens.
Huge batch size.
Really large, yeah.
And what about handling longer contexts, which are so critical for agentic tasks? Did they extend the context window during pre-training?
Yes, towards the end of pre-training, they included an annealing phase that was 400 billion tokens with a 4K sequence length, where the learning rate decayed further from 2E5 down to 76.
Okay.
This was followed by an additional 60 billion tokens trained with a 32K sequence length, really pushing the model to handle longer inputs during pre-training itself.
And then they got to 128K.
Right. Finally, the yarn method was then used after pre-training to extend the context window to that massive 128K,
Yeah.
making it highly capable of processing extensive documents.
And stability held throughout.
The paper explicitly highlights that the training loss remained smooth and stable throughout this entire process, with no observable spikes, which again speaks volumes about the effectiveness of NeoClip and their robust infrastructure.
So the pre-training laid an incredibly stable and efficient foundation. Now, how does Kimi K2 translate that foundation into the sophisticated agentic behaviors we've been discussing? Let's start with supervised fine-tuning, or SFT.
Okay, SFT. For supervised fine-tuning, they continue to employ the muon optimizer.
Sticking with muon.
Yeah, this decision aligns with their previous findings that a muon pre-trained checkpoint performs optimally when fine-tuned with muon. Makes sense.
Right.
A critical aspect here was the construction of their instruction tinning dataset. It was built with two core principles: maximizing prompt diversity to cover a wide range of tasks and ensuring exceptionally high response quality.
Quality being key for reliable agents.
Absolutely crucial, yes.
How did they generate such a high-quality, diverse dataset for SFT? It's not just about quantity here, is it?
You're right. Quality is paramount. They developed a suite of data generation pipelines, each specifically tailored to different task domains. These pipelines combined human annotation, sophisticated prompt engineering, and rigorous verification processes.
A multi-pronged approach again.
Yeah. They leveraged K1.5 and other in-house domain-specialized expert models to generate candidate responses,
Okay.
which were then subjected to automated quality evaluation and filtering by other LLMs or, sometimes, human judges. This systematic multi-step approach ensures a robust and high-fidelity dataset, crucial for teaching complex instructions and behaviors.
The paper highlights a large-scale agentic data synthesis for tool use learning as a major advancement. What exactly does that involve, and what makes it such a critical component for training truly capable AI agents?
This is absolutely critical because it enables LLM agents to autonomously use unfamiliar tools, interact with external environments, and iteratively refine their actions through reasoning, execution, and error correction.
Things you need for complex tasks.
It's exactly. Solving complex, multi-step tasks that require dynamic interaction with real-world systems inherently relies on this capability. Now, while real-world environments offer authentic signals, they're often difficult and costly to scale.
Right.
Kimi K2 addresses this by utilizing a sophisticated pipeline that simulates real-world tool use scenarios at scale, generating tens of thousands of diverse, high-quality examples that wouldn't be readily available otherwise.
Can you walk us through the stages of this data synthesis pipeline, as depicted in Figure 8? It sounds like a complex orchestration.
Certainly. It's a meticulously designed three-stage pipeline. The first stage is tool spec generation.
Generating the tools themselves.
Right. They constructed a comprehensive repository of tool specifications from two complementary sources.
Right.
Over 3,000 real model context protocol, or MCP, tools pulled directly from GitHub, giving them real-world examples.
So cool tool.
And systematically evolving over 20,000 synthetic tools.
20,000 synthetic tools. Wow.
Yeah. These synthetic tools are generated through a hierarchical domain evolution process, covering diverse categories like financial trading or robot control, each with clear interfaces and operational semantics. Figure 9's TSNE visualizations really show the broad diversity and complementary coverage of both the real and synthetic tools.
That's an incredible scale for tool creation, far beyond what you'd typically find. What comes after generating these thousands of tools?
The second stage is agent and task generation. They create thousands of distinct agents by synthesizing various system prompts and equipping them with different combinations of tools from their expansive repository.
So lots of different agent personalities and toolkits.
Exactly. This ensures a broad coverage of potential use cases and agent personalities. For each agent configuration, tasks ranging from simple to complex operations are generated, and each task is explicitly paired with a rubric.
A rubric?
Yeah. Specifies success criteria, expected tool use patterns, evaluation checkpoints. This rubric-based approach ensures consistent and objective evaluation of the agent's performance later on.
And the final stage is generating the actual interaction, the multi-turn trajectory generation. How do they simulate these complex dialogues and tool interactions?
Right. This stage simulates realistic tool use scenarios. It involves LLM-generated user personas engaging in multi-turn dialogues with agents, creating naturalistic interaction patterns.
Like a simulated conversation.
Pretty much. A sophisticated tool simulator acts as a world model, executing tool calls and providing realistic feedback, maintaining and updating the environment state after each tool execution.
Okay, it simulates the world's reaction.
Yes, and crucially, it introduces controlled stochasticity to produce varied outcomes, successes, partial failures, edge cases. This makes the generated data more robust.
Handles the unexpected.
Hopefully. Finally, an LLM-based judge evaluates each generated trajectory against the predefined task rubrics, retaining only high-quality data for training.
So it's mostly simulated, which allows for scale, but does it ever touch real environments to ensure authenticity?
Good question. It employs a hybrid approach with real execution environments.
Oh, okay.
While simulation provides scalability, they acknowledge its fidelity limitations. So, they complement the simulated environments with real execution sandboxes, particularly for coding and software engineering tasks.
Where ground truth matters a lot.
Exactly. These real sandboxes execute actual code, interact with genuine development environments, and provide ground truth feedback through objective metrics like test suite pass rates.
So you get the best of both worlds.
That's the idea. This combination of scalable simulation and targeted real-world execution generates diverse, high-quality tool use demonstrations that balance coverage and authenticity. It effectively implements large-scale rejection sampling through their rigorous quality filtering process.
This sounds like a robust approach to SFT, setting up the model for true agency. Now let's talk about reinforcement learning, or RL. The paper states that RL has better token efficiency and generalization than SFT. How is Kimi K2 scaling RL further to leverage these benefits?
Indeed. Building on their K1.5 work, Kimi K2 significantly scales RL in both task diversity and training FLOPs. To support this, they developed a gym-like extensible framework that facilitates RL across a wide range of scenarios.
Like OpenAI Gym.
Inspired by it, yeah. This framework is extended with a large number of tasks that provide verifiable rewards.
Verifiable rewards, clear right or wrong answers.
Exactly. But for tasks relying on subjective preferences, like creative writing or open-ended Q&A where verifiable rewards are difficult, they introduced that self-critique rubric reward mechanism we mentioned earlier.
Where the model judges itself.
Right, where the model performs pairwise comparisons to judge its own outputs. This allows tasks from various domains to benefit from the RL paradigm, extending beyond simple imitation.
Let's delve into these verifiable rewards. What kind of tasks fall under the verifiable rewards gym framework?
Okay, the verifiable rewards gym covers several key areas. For math, STEM, and logical tasks, their data prep follows two principles: diverse coverage and moderate difficulty.
Moderate difficulty, why not harder?
Well, they collect high-quality QA pairs from expert annotations, internal pipelines, open data sets. Difficulty is assessed by the SFT model's pass at K accuracy. They select only problems of moderate difficulty to ensure an optimal learning signal, not too easy, but not so hard. It overwhelms the model early on.
Makes sense. And for complex instruction following, where the model needs to understand nuanced requirements over extended dialogues.
For complex instruction following, which demands understanding implicit requirements and handling edge cases over long dialogues, they use a hybrid verification framework.
Hybrid again.
Yeah. Combining deterministic evaluation via code interpreters for clear white-wrong outputs with LLM as judge evaluation for more nuanced instructions, a crucial addition is a hack check layer.
Hack check.
To detect adversarial behaviors where models might claim they fulfilled the instruction without actually doing it.
Ah, sneaky models.
Can happen. Training data comes from expert-crafted prompts, agentic instruction augmentation inspired by AutoF, and fine-tuned models specialized in generating instructions that probe known failure modes. It builds a robust instruction-following capability.
How do they ensure faithfulness in responses, especially given that agents might generate their own reasoning chains?
Faithfulness is deemed essential, particularly in multi-turn tool use or self-generated reasoning chains where factual accuracy is paramount.
Can't have the agent making stuff up.
Definitely not. Inspired by the FACS-ETS grounding framework, they train a sentence-level faithfulness judge model. This judge effectively detects factual claims made without supporting evidence in the context.
Okay.
It serves as a reward model, to penalize ungrounded statements and thus enhance overall faithfulness performance.
And for the demanding coding and software engineering tasks, which are complex and require deep interaction with environments.
For coding and software engineering, they gather problems in judges from both open-source datasets and synthetic sources. To ensure diversity and correctness of reward signals, they incorporate high-quality human-written unit tests retrieved from pre-training data.
Using existing tests.
Yeah. For software engineering tasks specifically, they've built a robust development environment based on GitHub pull requests and issues, designed to mimic real-world development workflows.
A realistic sandbox.
A very realistic sandbox. It runs on a Kubernetes-powered infrastructure, supporting over 10,000 concurrent instances. Highly scalable for competitive coding and complex software engineering tasks, providing real-world feedback loops.
Finally, what about safety in the RL framework? How do they ensure the agentic models remain aligned and safe under adversarial conditions?
Safety enhancement begins with human-curated seed prompts covering prevalent risk categories, violence, fraud, discrimination, etc.
The usual suspects.
Right. To simulate sophisticated jailbreak attempts, they employ an automated prompt evolution pipeline. This pipeline involves an attack model generating adversarial prompts, a target model producing responses, and a judge model evaluating if the attack worked using a task-specific rubric.
An adversarial training loop for safety.
Essentially, yes. This iterative adversarial training helps build robustness against safety breaches.
Beyond verifiable rewards, the paper discusses a self-critique rubric reward mechanism. This sounds incredibly powerful. What problem does it solve that verifiable rewards can't?
Right. The self-critique rubric reward mechanism addresses the challenge of aligning LLMs with nuanced human preferences, things like creativity, depth of reasoning, conversational style.
The fuzzy stuff.
Exactly. The fuzzy stuff where objective verifiable rewards are difficult or impossible to define. Here, the model evaluates its own outputs to generate preference signals.
How is that bootstrapped?
K2's critic capability is bootstrapped, using a mixture of open source and in-house preference datasets. Its initial critic capability is actually developed during the SFT stage, giving it a starting point for self-evaluation.
So the model critiques itself to improve. How does that work in self-critiqued policy optimization?
In this process, K2's actor generates responses, and then the K2 critic ranks these responses by performing pairwise evaluations against a combination of rubrics.
What kind of rubrics?
These include core principles like clarity and relevance, conversational fluency, objective interaction, the fundamentals for Kimi as an AI assistant. Additionally, there are prescriptive rubrics like initial praise or explicit justification, which aim to stop reward hacking.
Ah, gaming the system.
Right. And also human annotated rubrics for specific instructional contexts. This allows for dynamic, continuous alignment with the model's evolving on-policy behavior, enabling it to learn from its own generated experiences.
And how is the critic model itself refined, aligned, assuring its judgments are accurate and not just self-serving?
That's the closed-loop critic refinement and alignment process. It continuously refines the critic model using verifiable signals from on-policy rollouts, specifically rollouts generated from those verifiable reward prompts we talked about.
Grounding the critic in objective data?
Exactly. This step is crucial because it distills objective performance signals from verifiable RL scenarios directly into the critic's evaluation model. This transfer learning grounds its more subjective judgments.
So improvements on clear tasks help it judge fuzzy tasks better.
That's the idea. It allows performance gains from verifiable tasks to enhance the critic's judgment on complex tasks lacking explicit reward signals. This closed-loop process ensures the critic continuously recalibrates its evaluation standards, leading to comprehensive performance improvements across user intent understanding, creative writing, complex reasoning areas where direct verification is elusive.
Are there any specific algorithmic additions to the RL process to further optimize training beyond these reward mechanisms?
Yes, there are three notable additions mentioned. First, budget control.
Budget control.
Yeah, RL often inadvertently leads to longer model responses as the model learns to maximize reward, which is sometimes okay for reasoning, but inefficient otherwise.
Right, rambling responses.
Exactly. To counter this, a per-sample maximum token budget is enforced based on task type, with penalties for truncation. This enhances token efficiency by incentivizing concise yet effective solutions.
Makes sense. And the second addition?
The second is the integration of an auxiliary PTX loss. This is crucial for preventing catastrophic forgetting of valuable high-quality data during joint RL training.
Forgetting the SFT data.
Potentially, yeah. By including high-quality samples from the original SFT dataset in the RL objective, it not only leverages their advantages but also mitigates the risk of overfitting to the limited set of tasks explicitly present in the RL training regime. It substantially improves generalization.
And finally, a temperature decay schedule. How does that fit in?
Yes. For tasks like creative writing or complex reasoning, a high sampling temperature is used in the initial stages of training.
To encourage exploration.
Right, to promote exploration and encourage the model to discover diverse and novel responses. However, maintaining a high temperature later in training can compromise reliability and consistency.
So you dial it back.
Exactly. A temperature decay schedule gradually shifts from exploration to exploitation, ensuring the model benefits from initial creative exploration while ultimately converging on stable, reliable, and high-quality outputs.
This entire RL framework sounds incredibly sophisticated, leveraging multiple reward signals and clever algorithmic tweaks. How is the underlying infrastructure supporting this complex RL training at such a large scale?
Their RL infrastructure uses a collocated architecture, meaning both the training and inference engines reside on the same workers, efficiently sharing GPU resources. This minimizes communication overhead between the actor and critic models. A centralized controller orchestrates data generation, training, parameter updates, creating a streamlined workflow. This hybrid setup is designed to optimize for throughput and reduce latency, critical as K2 scales. They also specifically addressed engine switching latency and failure recovery, common pain points in large-scale RL.
Efficient engine switching is crucial for seamless operation. How do they handle large-scale parameter updates between training and inference engines, especially when they might have different sharding schemes?
This is a significant challenge. Instead of, say, impractical network file system solutions for parameter sharing, they developed a distributed checkpoint engine co-located directly on the training nodes to manage parameter states.
Okay, a dedicated checkpoint engine.
Right. To update parameters, each checkpoint engine worker first gets a local copy of the full parameter set from the training engine, then broadcasts this full set across all other checkpoint engine workers.
Broadcasts the whole thing?
Yeah. The inference engine then retrieves only the specific parameter shard it requires. Figure 10 illustrates this. To minimize memory footprint during this broadcast, updates are performed parameter by parameter in a pipeline manner, detailed in Appendix G.
So they broadcast the full parameter set, even if individual inference workers only need a shard. That seems counterintuitive for efficiency.
It might seem so at first glance. While this transfers more data than a theoretical transfer what you need method, it results in a simpler system design that fully decouples the training and inference engines, reducing interdependencies.
Simplicity wins.
And speed, apparently. Crucially, this approach, by minimizing synchronization overhead and maximizing network bandwidth utilization through the broadcast, actually outperforms the more granular transfer method in practice, according to the paper.
Really?
Yeah. The result is that a full parameter update for Kimi K2 can be completed in less than 30 seconds, which is negligible for a typical RL training iteration. Figure 13 shows this speed.
Impressive. And what about efficient system startup? Given the susceptibility of large-scale training to failures and the desire for rapid iteration.
To optimize startup, training workers selectively read parts of parameters from disk and then broadcast necessary parameters to peers. This ensures all workers collectively read the checkpoint only once.
Okay.
For inference engine startup, the checkpoint engine is cleverly reused. It collectively reads the checkpoint from disk and then updates the uninitialized inference engine. This design makes the system robust to single-point failures.
So an inference replica can restart quickly.
Exactly, without needing to reload the entire model from scratch, significantly improving reliability and iteration speed.
Finally, what optimizations are in place for agentic rollout, especially for long-horizon, multi-turn tasks that can be very computationally intensive?
Agentic rollouts present distinct challenges, yeah. Complex environmental interactions, prolonged durations, they employ several strategies.
Such as?
First, deploying heavy environments as dedicated services for easier scaling and resource management. Second, using a large number of concurrent rollouts to amortize latency from expensive interactions, ensuring high throughput.
Keeping the GPUs busy.
Right. And third, utilizing a partial rollout technique to pause and resume long-tail unfinished tasks, preventing them from blocking the entire process and maximizing computational efficiency.
Handling the stragglers.
Yep. To enhance research efficiency, they've also designed a unified interface inspired by OpenAI Gem to streamline the integration of new environments. And they have clear plans to scale their RL infrastructure to even more diverse interactive environments in the future.
We've covered the intricate details of Kimi K2's pre-training and post-training innovations. Now, let's look at the results. How does Kimi K2 Instruct perform its post-training evaluations across various benchmarks?
Okay, results time. The evaluation settings are quite broad, encompassing coding, tool use, reasoning, long context, factuality, and general capabilities. They benchmarked against both open source and proprietary frontier models.
Comparing against the best.
Right. And crucially, ensuring all candidates were evaluated under their non-thinking configuration.
To avoid gains from extra test time compute.
Exactly, making it a fair comparison. Output token limits were carefully set, and repeated sampling, AVG at K, was used for stable scores, especially on high-variance benchmarks. Context windows were set to 128K tokens where applicable, leveraging Kimi K2's long context capabilities.
So if I'm hearing this right, Kimi K2 isn't just excelling in one area, it's showing remarkable state-of-the-art performance across the board. What are the top 2 or 3 results that truly highlight its prowess in agentic and competitive coding?
You're absolutely right. It's the breadth of performance that's striking. Referencing Table 3, Kimi K2 Instruct demonstrates state-of-the-art open-source performance on real-world software engineering tasks.
Like SWE Bench.
Exactly. On SWB Bench verified agentic single attempt, it scored 65.8%. And remarkably, with multiple attempts, it reached 71.6%.
That's huge for open source.
It is. It substantially closes the gap with Claude 4 Opus, which scored 72.5% and 79.4% respectively. On SWE Bench Multilingual, Kimi K2 Instruct achieved 47.3%, making it the SOTA open source model and competitive with Claude 4 Sonnet's 51.0%.
Strong multilingual coding, too.
And it led all models on Live Code Bench v6 with 53.7%. These numbers are a clear indication of its strong capabilities in complex practical coding tasks.
That's very strong performance in software engineering, a domain where true agentic capabilities are highly valued. What about its general agentic tool use capabilities? How does it measure up there?
Kimi K2 Instruct sets a new standard on multi-turn tool use benchmarks. It achieves 66.1% pass at 1 on Ta2 Bench and 76.5% on Ace Bench.
Substantially outperforming baseline.
Yeah, substantially outperforming all baselines and remaining highly competitive with GPT 4.1's 80.1% on Ace Bench. This performance affirms its strength in grounded, controlled, and agent-driven tool orchestration across various domains. It shows it can effectively integrate and leverage external resources.
And for general capabilities, outside of those highly specific agentic tasks, how does Kimi K2 Instruct perform across a broader range of benchmarks?
Kimi K2 Instruct exhibits strong, balanced performance across general knowledge, math, instruction following, and long context tasks. It surpassed open source peers on Simple QA at 31.0%, MMLU at 89.5%, and MMLU Redux at 92.7%.
Beating GPT 4.1 on MMLE Redux.
Notably, slightly ahead of GPT 4.1 on the latter, yeah. It leads all models on instruction benchmarks, scoring 89.8% on IFEVL and 54.1% on multi-challenge, outperforming even GPT 4.1 and Claude Opus 4 in certain aspects there.
Very strong instruction following.
And in math and STEM, it achieves top-tier scores like 69.6% on AIM 2024 and 75.1% on GPQA Diamond. These results collectively position Kimi K2 Instruct as an exceptionally well-rounded and capable generalist, not just a specialist in agentic tasks.
What about open-ended evaluations, which often reflect real-world user preference and practical utility?
Good point. On the LMSYS Arena leaderboard, as of July 17, 2025, Kimi K2 Instruct ranked as the top 1 open source model and 5th overall based on over 3,000 user votes.
Top open source on the Arena, that's significant.
It's a significant real-world preference signal, demonstrating strong user satisfaction across diverse blind prompts. Furthermore, on the Arena Hard Auto v2.0 benchmark, it achieved state-of-the-art win rates on both hard prompts at 54.5% and creative writing tasks at 85.0%.
Handling hard and creative prompts well.
Right, showcasing its ability to handle challenging and nuanced requests. And, as Figure 11 illustrates, on a Chinese in-house benchmark, Kimi K2 Instruct showed strong performance with high win rates against ChatGPT 4o latest and Claude Sonnet 4.
Indicating strong multilingual capabilities, too.
Exactly, which is a major plus for global applications.
Moving to the pre-training evaluations for Kimi K2 base, what did they find about its foundational capabilities before all the fine-tuning?
Okay, the base model. For Kimi K2 base, they used a variety of benchmarks covering general language understanding, coding, math reasoning, and Chinese language capabilities. They compared it against leading open-source foundation models like DeepSeek v3 base, Qwen 2.572b base, and Llama 4 Maverick.
The usual suspects for base models?
Right. Evaluation configurations included both perplexity-based and generation-based assessments to provide a comprehensive picture of its raw capabilities.
And the results, how does the base model stand on its own?
Table 4 summarizes these foundational strengths. Kimi K2 base achieved state-of-the-art performance on 10 out of 12 English language benchmarks for general understanding.
10 out of 12 SOTA, wow.
Yeah, notable results like 87.79% on MLU and 35.25% on Simple QA, significantly outperforming all baselines. For coding, it set new standards, leading across all metrics. For instance, 74.00% on CRUX Evaluate and 80.33% on Evil Plus.
Elena base coding too.
And in mathematical reasoning, it exhibited exceptional capabilities, leading on 3 out of 4 benchmarks, including 70.22% on math and 92.12% on GSM-8K.
Very strong math base.
Critically, it demonstrated superior multilingual capabilities by achieving state-of-the-art results across all Chinese language benchmarks, like 92.50% on CEVAL and 90.90% on CMLU. These results confirm a very strong pre-trained foundation.
Finally, let's touch on safety. How did Kimi K2 fare in safety evaluations, and what were the experiment settings they used to test its robustness?
Safety evils. They conducted extensive red teaming evaluations on Kimi K2 and compared it with other open-source LLMs like DeepSeek V3, DeepSeek R1, and Qwen 3.
Okay.
The evaluation covered harmful, privacy, and security content using various attack strategies: basic, prompt injection, iterative jailbreak, and crescendo.
Crescendo sounds ominous.
It's designed to be progressively harder. They utilize prompt foo to generate adversarial prompts, creating 3 attack prompts per plugin for each strategy. Some combinations also included Chinese prompts to test multilingual robustness. Manual human review was integrated to minimize subjectivity.
What were the key findings from these safety evaluations, as shown in Table 6? Were there any surprises in how it held up?
The results showed varying trends. Under the base 64 encoding strategy, passing rates generally approached or reached 100%. Simple encoding didn't fool it much. In contrast, the crescendo strategy, the escalating one, led to a general drop in passing rates across models, suggesting its stronger adversarial effectiveness.
As expected, maybe. How did Kimi K2 do specifically?
Kimi K2 showed relatively higher passing rates on some complex cases, like harmful iterative jailbreak, compared to other models that didn't have specific targeted optimization for these sophisticated scenarios.
So some resilience there.
Some resilience, yeah. The report does acknowledge limitations, though, like the inherent subjectivity of human review and the limited relevance of some API misuse tests for base LLMs. Those are more suited for evaluating agent models with full tool calling capabilities, not just the base model.
So we've seen the impressive capabilities and the rigorous development behind Kimi K2. But no model is perfect, especially at the bleeding edge. What limitations did the team identify in the current Kimi K2 models?
Right, Section 5 covers this. The paper explicitly lists several practical limitations they've identified. First, when dealing with very hard reasoning tasks, or if two definitions are unclear, the model may generate an excessive number of tokens.
Gets too verbose.
Yeah, and this can unfortunately lead to truncated outputs or incomplete tool calls, hindering its ability to fully resolve the task.
Okay, that's a practical issue.
Second, they observe that performance can actually decline on certain tasks if tool use is unnecessarily enabled.
Using tools when it shouldn't.
Right. If the model attempts to use tools when they're not beneficial or required for a given task, it can complicate the process rather than streamline it.
Interesting trade-off.
And finally, for building complete software projects, they found that the success rate with one-shot prompting is not as good as when Kimi K2 is used under a more comprehensive external agentic coding framework.
So it needs that external scaffolding for big projects.
That seems to benefit significantly from it, yeah.
These sound like practical limitations that could directly impact real-world deployment and user experience. What's the future outlook, according to the team? How do they plan to address these and continue pushing the boundaries?
The Kimi team states they're actively working to address these identified limitations in future releases, indicating a commitment to continuous improvement.
Good to hear.
A major part of their future vision involves the strategic open sourcing of Kimi K2's base and post-trained checkpoints. We talked about this. It's a deliberate move designed to spur further progress in agentic intelligence within the broader research community.
Fueling the ecosystem.
Exactly. They also have explicit plans to continuously scale their RL infrastructure to even more diverse interactive environments, leveraging that unified interface they've developed, pushing the boundaries of what these agentic models can do by providing them with richer, more complex interaction spaces.
What a deep dive this has been. We've unpacked Kimi K2's monumental contributions, starting with its stable, token-efficient pre-training made possible by the novel muon clip optimizer.
Yeah, and that staggering 15.5 trillion tokens of meticulously retraced data.
Right. The insight here is a clear shift towards proactive, intelligent data engineering, moving beyond just passive data consumption.
And we then saw how this foundation is built upon through sophisticated multi-stage post-training. This includes that large-scale agentic data synthesis pipeline, creating high-fidelity tool use demonstrations.
Really pushing the envelope on how we train models for complex interactions.
Definitely. And a generalized reinforcement learning framework that ingeniously combines verifiable rewards with that self-critique mechanism for open-ended alignment in nuanced domains.
The results speak for themselves. Kimi K2 demonstrates state-of-the-art performance across agentic, coding, mathematics, and reasoning benchmarks. It truly solidifies its position as the most capable open-weight LLM to date,
Significantly closing the gap with proprietary models in non-thinking settings, which, as you said, is a huge win for the open source community.
This isn't just another incremental improvement, is it?
Now, Kimi K2 isn't just another model. It's arguably a blueprint for the next generation of AI agents. Its open source release fundamentally alters the landscape for researchers and practitioners in ML, data science, and mathematics.
Providing a powerful new foundation to build upon.
Exactly, and truly democratizing access to cutting-edge agentic capabilities.
So what does this all mean for the future? With Kimi K2 pushing the boundaries of open agentic intelligence and making these capabilities widely available, what new complex problems will you, the listener, be able to solve?
Yeah, and what unforeseen applications will emerge as this powerful technology is unleashed into the world.
Indeed. The possibilities are vast and exciting, inviting the community to explore this new frontier.
Absolutely.
That's all the time we have for this deep dive. Thank you for joining us, and we look forward to exploring more groundbreaking research with you next time.